Hello, and welcome to this exercise in which we fit a polynomial regression model to data in RStudio. These data derive from a study by Jones and colleagues in the British Medical Journal, and their work was concerned with decayed, missing and filled teeth in children and how that might relate to the fluoride concentration in the water that the children were drinking. They looked at 21 populations of children and they had an index. It's the decayed, missing or filled teeth per 100 children against the fluoride concentration in water in terms of parts per million. I've read these data in, and now we need to go and fit a variety of models to work out the most appropriate predictive model. So the first thing we should be doing is, of course, plotting our relationships. So this is just what we're going to be doing here. In terms of fitting a model, first of all, we need a y response variable, and that is the decayed and missing teeth index. Here we need also a predictor variable, and that's the fluoride concentration in parts per million. Now, to do this analysis in terms of fitting more and more complicated models, it will help to actually define x squared and x cubed. And since we've defined x in this way, I'm simply going to define x squared in that way too. It's the square of x. The cube of x is, of course, x raised to the power 3. So all individual x observations are now cubed, and we've created another vector for x cubed. And just to be on the safe side, we're going to be looking at x to the power 4. Now let's simply plot a graph of the relationship between x and y. So this is what we do here, and we find that there is apparently a relationship between this DMF index and the fluoride concentration, and it appears somewhat non-linear overall. Now, to begin with, we'll fit a linear model to these data. How do we go about doing that? Well, we can call up the GLM routine for simply putting a relationship between y and x. We can then examine whether x explains variability in y by asking for the analysis of variance breakdown. And here what we can see is that the x value explains significant variability in y, in that the probability of us getting that test statistic or more extreme, if the null hypothesis of there being no relationship is actually really very small, so we reject the null hypothesis. Now we can fit that model that we have actually calculated and estimated back onto the graph by simply using the abline command here. And this is what I'm doing here, and we'll see that the fitted model now appears on the graph. So this is what we've done here. Now you will note that there is some curvature in that relationship, so perhaps a higher order model would be a better predictive model. We can fit a higher order model by simply saying, for example, in this case, fit2 is the linear model of y and how it's related to x and x squared. And likewise, we can look at the analysis of variance breakdown of this model. And this is what we get here. So, with a type 1 sum of squares, we know that x explains significant variability in y, but here the x squared term explains significant variability above and beyond that explained by x. This is the beauty and value of a type 1 sum of squares, a sequential sum of squares, in that as we are building our model of increasing complexity, we are asking in each case whether that additional complexity is justified in terms of explaining additional variability in the model over and above the simpler model. So let's now fit this model to the graph and see how that actually looks. To do so, what we need is to define a variable xv, which is x values, and I'm going to go from the minimum value of x that was observed to the maximum and take it in small steps of 0.01. What is the yv? Well, the y comes from the predicted fit of the model, and here is how we will specify that. The yv is predict from fit 2, because fit 2 is the fit of the linear model, and one of its properties is that we can now predict based on that fitted model and the coefficients that have been estimated. And here we are putting x as xv and the x squared term that we have fitted as xv squared. And now we can simply draw those lines on, and I'm drawing them in green, and we will see here that we have explained some of that curvature in our data. We've got this nice fit of a quadratic. Well, we might think, well, what about an x cubed term? Could we fit a more complicated model? Well, of course we could have a go, and here is the fit of the more complicated model. So this has x, x squared, and x cubed. You will note that we've not gone for just a model of x and x cubed, say, that we've respected the hierarchy in that we have, by including x cubed, we are also necessarily including a model with x squared and x in as well. So there's the fit 3. There's the analysis of variance for the fit of that model 3. X explains significant variability in y. X squared explains significant variability in y once you take into account the variability explained by x itself. But x cubed fails to explain significant variability over and above that explained by x and x squared. So we're left with a view overall that the quadratic, the model with x and x squared, is superior because adding that extra term does not explain significant variability in the model. Now let's have a look at the fitted model of the x cubed term. Here again I'm defining xv. I didn't really need to redefine it that way because it's defined above. Yv is now the prediction from the fit of that third level, the cubic model, and of course x, x squared, and x cubed from that third model come now from the x values that we are exploring, and we want to join them, and I've actually drawing them there in black. Well, we can see that, of course, because it's a cubic model, we do have curvature, but I hope you can see that the fit of the cubic model and the fit of the squared model seem really very, very similar, and part of the similarity arises from the fact that that cubic term really doesn't explain much of the additional variance above and beyond that explained by x and x squared. So we're left with just one more thing now, and that is just to establish whether the underlying assumptions of the fit of our general linear model are appropriate. Since we've gone for the quadratic model, I'm just going to choose the quadratic model in this case. And the first thing is I'm going to be looking at the residuals, and the residuals look pretty dandy to me in terms of there being no overall strong pattern. If we had fitted the linear model, we might have seen some pattern in those residuals, because in effect we're fitting the wrong model to the data, since there was clearly curvature there. And here we can of course examine the normality, and overall the distribution of the residuals appears relatively normal. Thank you for listening to this R-Labs tutorial video. If you found this useful, you might be interested in our free online Moodle course, or check out and subscribe to our YouTube channel.